All right, let's just jump right into it. What if I told you that one of the most fundamental things you learned in school, something you feel every single second of every day, is just flat out wrong? Yeah, today we're going to completely dismantle your lifelong understanding of gravity. And here it is, the big idea. According to the general theory of relativity, gravity is not a force. I mean, just think about that. Einstein is saying gravity is basically an illusion. There's no invisible force field pulling you down. So what on earth is actually going on? Okay, to get our heads around this really radical idea, we got to start where Einstein himself started. And that's with something he called, get this, the happiest thought of his entire life.
So why was this so happy? I mean, it doesn't sound very happy, right? A guy falling from a roof, but it wasn't about his unfortunate situation. The begin sight was that while this guy is falling, he would feel completely weightless, you know? If he dropped his keys, they'd just float there right beside him. His whole experience would be just like
an astronaut floating out in deep space, miles away from any planet. Now, this is where Einstein made his genius leap. He said, look, these two situations aren't just similar, they are physically, totally, 100% identical. You literally couldn't tell the difference. This is his famous equivalence principle.
So that astronaut in deep space, they're the textbook definition of an inertial observer. They aren't accelerating, they feel zero forces acting on them, so if the situation is identical to the falling man's, then the conclusion is, well, it's pretty mind-blowing. It means the falling man is also an inertial observer. He isn't accelerating.
And I know what you're thinking right now. You're screaming. Of course he's accelerating. His speed is picking up by 9.8 meters per second times every second. But if we just trust Einstein's principle for a minute, it flips this whole question completely on its head.
So if the falling person isn't the one accelerating, what about you? Right now, sitting there, listening to this. Think about it. The falling man feels totally weightless. But you don't, do you? No, you feel your chair or the floor pushing up on you. And according to Einstein, if you can feel a force like that, you're the one who's not inertial. You are the one who's actually accelerating.
And there it is. That's the big switcheroo. The person in free fall is just following their natural straight-line path through the universe. It's you, on the other hand, who's being stopped from following that path. The ground is pushing up on you with a constant force. Therefore, you are the one constantly accelerating upwards.
So the key takeaway here is that acceleration, in this new way of thinking, is any deviation from your natural path through space-time. The floor is constantly stopping you from taking that natural path, so it forces you to accelerate. And the only reason you aren't just flying off into space is, well, because in curved space-time you actually have to accelerate upwards just to stand still. Wild, right?
Okay, so let's pause. If gravity isn't a force pulling us down, and the only real force is the ground pushing us up, then we have to answer the most obvious question of all, don't we?
Yeah, if there's no force pulling stuff down, why does an apple fall from a tree? Why do things move towards the earth when we let them go? Well, the answer has absolutely nothing to do with a pull, and everything to do with the actual shape of the universe itself.
Think about it like this. Imagine two people standing on the Earth's equator 1,000 kilometers apart. They both start walking due north in perfectly straight lines. They never, ever turn left or right, and yet, what happens? They will eventually meet at the North Pole. It would totally look like some mysterious force was pulling them together, but there wasn't one. They were just following straight lines on a curved surface. And that right there is exactly how gravity works. This famous quote from physicist John Archibald Wheeler just sums it all up so perfectly. Matter tells spacetime how to curve, and spacetime tells matter how to move. Massive things, like the Earth, literally warp the fabric of spacetime around them. And other objects, they just follow the straightest possible path, which is called a geodesic, by the way, through that curved spacetime. What we feel as the force of gravity is just matter following the straightest path it can through a curved universe. Now, I get it, this might all sound like some kind of philosophical word game, but general relativity isn't just a cool idea. It makes real, concrete, testable predictions, and they're totally different from Newton's old ideas about gravity. Just take that classic old mystery. Why do a feather and a bowling ball fall at the exact same rate in a vacuum? Well, Newtonian physics kind of shrugs and says it's a coincidence that an object's gravitational mass just happens to be identical to its inertial mass. But in general relativity, there's no coincidence. There's no mystery at all. Of course they fall together. They are both just following the very same straight-line path through space-time. It's the only path they can take.
But the ultimate test, the real showdown, came in 1919. See, Einstein predicted that the sun's enormous mass should curve spacetime so much that it would actually bend the path of light from distant stars passing by it. The only way you could possibly see this, though, was during a total solar eclipse. So an astronomer, Sir Arthur Eddington, led this big expedition, took the photos during the eclipse, and the results were just staggering. The starlight was bent. Einstein was right.
And here's the kicker. It wasn't just bent by some random amount. The amount of bending they observed was exactly what Einstein's theory predicted it would be. And, more importantly, it was precisely double the amount that a simpler Newtonian model would have suggested. This was a huge, stunning confirmation. Spacetime, it really is curved.
So, let's wrap this up by bringing it all back to our new, kind of weird understanding of acceleration. Physics tells us a pretty solid fact. A charge that is accelerating should radiate energy. And this leads to a really fascinating final puzzle for you.
So just think about this for a second. An accelerating charge radiates energy. So which one radiates? A charge just sitting still on a table or a charge that's in free fall? Your answer reveals everything. If you believe the old Newtonian view, the falling charge is accelerating, so it should radiate. But if you believe general relativity, the falling charge is actually inertial. It's just coasting. And the charge sitting still on the table, that's the one that's truly accelerating upwards, so it should be the one to radiate. What you believe happens here, well, that reveals what you truly think about the very nature of gravity. Is it a real force, or is it all just an illusion of space-time?